Definitions of cost estimate characteristics, clarifying the primary and secondary parameters that define estimate maturity and usage. Understanding the various characteristics that define and differentiate cost estimates is essential for applying the classification system effectively. These characteristics are grouped into 1 primary and 4 secondary attributes. The primary characteristic, the level of project definition, drives the classification category. The secondary characteristics, end usage, estimating methodology, expected accuracy range, and preparation effort, are typically aligned with the degree of project definition. Primary characteristics, level of project definition, refers to the percentage completion of project engineering and documentation, represents the availability and maturity of input deliverables such as scope definitions and functional requirements, preliminary or detailed drawings and specifications, equipment lists and calculations, lessons learned from past projects or reconnaissance data. Varies significantly by industry. Process industries are equipment-centric. Architectural projects are structure-centric. Software projects are function-centric. The completeness of these inputs governs the precision and reliability of the estimate. Secondary characteristics. End usage defines the intended purpose of the estimate at a particular project stage. Evolves as project maturity progresses. Class 5 and 4 used for strategy, concept screening, and feasibility. Class 3 supports budget authorization and control planning. Class 2 and 1 used for procurement, contract bidding, or final cost checks. Stakeholder perspective influences interpretation. Owners may use an estimate for funding decisions. Contractors may use the same class for bid formulation. Estimating methodology describes the technique used to derive cost projections, typically progressing with project definition. Stochastic methods, based on statistical, inferred, or heuristic models. Suitable when scope is not well defined. Quick to execute but carry greater uncertainty. Deterministic methods, based on direct quantification, e.g., material takeoffs, labor hours. Require detailed scope definition. Preferred for precision and final estimates. In some cases, stochastic methods may be used even at higher definition levels if they are efficient and adequately accurate. Expected accuracy range indicates how much the final cost might deviate from the estimate, traditionally expressed as a percentage range, e.g., minus 30% at a given confidence level, influenced by several factors: maturity of input deliverables, complexity or novelty of technology, quality of reference cost data, skill and experience of the estimator. Accuracy is not fixed by class but trends toward tighter ranges as classification progresses from Class 5 to Class 1. Must be evaluated in conjunction with risk and uncertainty assessments. Effort to prepare estimate reflects the time, cost, and resources needed to produce the estimate, not to be confused with project design effort. Increases with the volume and complexity of input information. Nonlinear relationship with project size. Larger projects may require relatively lower percentage effort. May be significantly reduced through use of automated design estimate tools in repetitive or modular project types. Summary. These characteristics form the foundational logic behind estimate classification. The level of project definition acts as the central axis around which the other attributes align. Understanding and clearly communicating these factors ensures that estimates are used appropriately, evaluated realistically, and aligned with the level of project certainty, reducing risk, misinterpretation, and inefficiency across all project stakeholders. Relationships and variations of estimate characteristics, interdependencies, flexibilities, and cross-influences within the estimate classification framework. While each cost estimate class is formally defined by its degree of project definition, real-world application of the classification system involves nuanced relationships and practical variations across secondary characteristics. These interdependencies allow flexibility, but also demand careful consideration, especially when comparing estimates across projects, industries, or stakeholder perspectives. Overview of interrelationships. The level of project definition is the dominant factor influencing all other characteristics. Secondary characteristics, usage, methodology, accuracy, and effort tend to trend consistently with project maturity, but are not rigidly fixed. Variability arises due to differences in project type and industry, technological maturity, estimator experience and methods, stakeholder intent and context. Characteristic interactions and variations. One, level of project definition drives maturity classification and governs what information is available, supported by a typical set of deliverables which vary by sector. Process industry, equipment specifications and P&IDs, architectural projects, floor plans, elevations, material schedules, software projects, functional requirements, user interface logic. The completeness and reliability of these inputs directly affect the feasibility of using deterministic versus stochastic methods. 2. End usage, often misunderstood or miscategorized when viewed without considering project maturity. A single estimate may serve different functions for different stakeholders. An owner's feasibility study may be a contractor's early stage bid. Terminology such as budget, preliminary, or bid may be misleading unless contextualized by classification. 3. Estimating methodology. Selection is influenced by available data, required precision, and effort constraints, though deterministic methods typically appear at higher classes. A well-calibrated stochastic model may yield acceptable accuracy even at Class 2 or 1. Hybrid methods, e.g. deterministic core with stochastic allowances, are common in transitional stages like Class 3. Methodology is often shaped by organizational preference or tool availability. 4. Expected accuracy range, not guaranteed by classification alone. Accuracy is also dependent on input data maturity, scope clarity and technology stability, market volatility and pricing assumptions. Accuracy ranges are typically narrower as class number decreases, but first-of-a-kind projects with high technical uncertainty can still have wide ranges even at Class 1. Repetitive projects with rich historical data may show low variation even at Class 3. 5. Effort to prepare estimate generally increases with project maturity and deliverable volume. Subject to exceptions, automated tools may generate Class 3 level outputs from minimal inputs in modular or design template-based projects. Larger projects tend to benefit from economies of scale. Percentage effort reduces as total cost increases. Metrics usually exclude effort invested in developing project documentation itself. Summary. The estimate classification system is structured but not rigid. Its effectiveness lies in understanding the dynamic interplay between project maturity and the associated estimating parameters. While the level of project definition provides the backbone of classification, the secondary characteristics introduce contextual flexibility that must be navigated thoughtfully. Recognizing these variations ensures estimates are neither over-trusted nor prematurely dismissed, and that each estimate's context, methodology, and risk are transparently communicated and properly interpreted. The scope of cost estimate preparation. Defining the boundaries, deliverables, and inclusions for estimate development in process industry projects. A well-defined scope of work is essential for the consistent preparation of project cost estimates. In process industries such as chemical, hydrocarbon processing, pulp and paper, and utilities, the cost estimating process is distinct from engineering or design and includes specific activities aligned with project lifecycle needs. The following outlines the key inclusions and exclusions that define the scope of estimate preparation, ensuring clarity, efficiency, and consistency across estimation teams and stakeholders. Core activities included in estimate preparation: establishing estimate requirements. Engage with the project team and client to understand the specific objectives and constraints of the estimate. Define the estimate's scope, timing, deliverables, and usage, e.g. feasibility, budgeting, tendering. Planning and structuring the estimate. Develop the work breakdown structure, WBS, and cost coding reporting framework. Prepare the estimating plan detailing timeline, resource allocation, tools, and deliverable formats. Quantification and costing. Conduct quantity takeoffs and cost the scope of work using input deliverables from engineering or design teams. Incorporate cost data from internal databases, vendor quotations, market intelligence, and historical benchmarks. Risk analysis and contingency estimation. Assess potential cost variances due to risk factors through methods such as range estimating, risk-weighted analysis, or Monte Carlo simulation. Allocate appropriate contingency within the estimate. Documentation and reporting. Prepare a comprehensive basis of estimate (BOE) report that defines all assumptions, methodologies, exclusions, and scope coverage. Format the estimate in alignment with project and corporate requirements for traceability and review. Estimate, review, and benchmarking. Facilitate internal reviews with peers and management, and align the estimate with past project benchmarks or norms. Implement changes and adjustments based on review outcomes. Issuance and handover. Finalize and issue the estimate to the project team as the basis for budgeting, scheduling, or contracting. For contractor-side estimates, this step may include bid pricing and markup strategies tailored to commercial positioning. Overhead and indirect support functions, typically included indirectly. Research and maintenance of estimating databases and benchmark libraries. Development of internal procedures, tools, and algorithms for consistent estimating practices. Training and upskilling of estimating personnel. Coordination and communication with project team, vendors, and third parties. General office overhead, e.g. facilities, utilities, IT support, administrative assistance. Functions explicitly excluded from estimate preparation scope. Engineering or design work. Any effort related to the creation of estimate input deliverables, e.g. P&IDs, layouts, datasheets, falls under engineering or project design, not estimating. Formal value engineering studies. While estimators may apply value-focused judgment, structured value engineering workshops are excluded. Advanced simulation and optimization. Activities such as lifecycle costing, system-level optimization, or complex scenario modeling are outside the standard scope. Tool database development for one-off cases. The creation of specialized tools or datasets for unique projects is not typically included. Project cost control and scheduling support. Ongoing project execution support functions are beyond the scope of estimate preparation. Skill level assumptions. Cost estimating activities are assumed to be performed by professional estimators or cost engineers, sometimes supported by clerical staff. For small-scale or early-stage estimates, a single multi-skilled individual may manage the entire process. Larger, more detailed estimates may involve a lead estimator, technical specialists for piping, civil, electrical, etc., support for takeoffs and documentation. In smaller firms, estimators may double as business owners, combining estimating with strategic pricing decisions. The scope of estimate preparation is clearly delineated to isolate it from adjacent functions like engineering or project management. By focusing exclusively on the tasks directly involved in quantifying and costing a project scope, this boundary ensures accurate estimation metrics, benchmarking validity, and transparency in project budgeting. Clear inclusion and exclusion criteria also facilitate consistent estimator workload measurement, tool deployment, and productivity assessments across varying project types and scales. Analysis of sources, examining the reliability, limitations, and patterns in published estimate preparation cost data. To develop a consistent understanding of estimate preparation costs in process industry projects, a wide range of published and private data sources were examined. While collectively useful, these sources revealed significant variation in content quality, coverage, and presentation methods. This section explores the nature of those discrepancies, identifies the contributing factors, and highlights consistent trends that inform best practices in estimating cost benchmarks. Observed variations in source data. 1. Undefined or inconsistent scope of estimating functions. Many references failed to clarify the scope of work considered as estimate preparation. Some included engineering or design work required to produce estimating deliverables. Others excluded it entirely. There was inconsistency in whether overhead research, database maintenance, and administrative support were considered part of preparation cost. 2. Outdated and normalized data. A substantial portion of the data originated in the 1960s, 1980s, and was adjusted to a common baseline, e.g. 1997 USD. Normalization techniques varied, with some sources producing conflicting results from similar base data. Technological advances, e.g. spreadsheets, commercial estimating tools that should theoretically increase productivity, were not always reflected in the data. 3. Unclear project scope. Some estimates applied only to field direct costs, while others included total installed cost, TTIC, or full EPC scope. Without clarity on whether owner costs, indirects, or home office costs were included, comparisons were unreliable. Number 4, ambiguity in estimate purpose. Sources often failed to specify whether estimates were developed for internal budgeting, contractor bidding, or client reporting. This made it difficult to evaluate whether effort levels corresponded to typical expectations for a given estimate class. 5. Lack of process and technology context. Project complexity, technological novelty, and scope repetition, e.g. modular versus custom, were rarely detailed. As such, high or low preparation costs may have been driven by these factors, but were not documented explicitly. 6. Missing detail on team skill and estimate quality. Data sets did not describe the experience level of the estimators or the quality control processes in place. Variability in estimator competence and methodology likely contributed to significant data scatter. 7. Inconsistent use of estimate classifications. Different terminologies and classification systems were used to describe estimate types, e.g., preliminary, budget, detailed, making alignment with modern class definitions, e.g., Class 5 to 1, challenging. Consistent trends identified. Despite the inconsistencies, several meaningful patterns were observed across data sources. Nonlinear cost-size relationship. Estimate preparation costs as a percentage of total project cost decrease with increasing project size due to economies of scale and fixed base effort. Complexity drives cost. Projects with advanced or novel process technologies consistently required more estimating effort than repetitive or well-understood systems. Effort increases with project maturity. Preparation costs correlate with the level of project definition. Class 1 estimates require significantly more effort than Class 5 estimates. While the published data on estimate preparation costs in process industries is fragmented and often lacks context, it offers enough directional insight to support useful benchmarks and trends. Estimators should approach such data with caution, interpreting it in light of scope, complexity, estimate class, and estimator capability. When used correctly, these insights help identify outliers, validate internal estimating performance, and support the calibration of effort norms for different project scenarios. Analysis of variations, quantifying the impact of project definition, size, complexity, and team structure on estimate preparation costs. While published data on estimate preparation costs exhibited significant scatter, a deeper review of influencing variables reveals distinct trends that explain much of the variation. This analysis categorizes and quantifies the primary factors that drive estimating effort and cost in process industry projects. Understanding these variations allows estimators to benchmark more accurately, allocate resources efficiently, and apply informed adjustments when planning estimating scope and budgets. 1. Variation with level of project definition, estimate classification. Estimate preparation costs increase as the project moves from conceptual to detailed definition stages. More complete input deliverables, e.g. layouts, equipment lists, specifications, require greater effort in validation, integration, and documentation. Relative effort indices normalized to Class 5 equals 1.0 illustrate the escalation in cost. Class 5, 1.0 baseline, Class 4, 2.6 to 4.0, Class 3, 3.5 to 10.0, Class 2, 14.0 to 25.0, Class 1, 19.0 to 50.0 plus. The wide range at higher classes reflects sensitivity to team structure, estimator quality, and project complexity. 2. Variation with project size. Estimating costs rise in absolute terms with project size, but decrease as a percentage of total project cost. This nonlinear trend reflects a fixed base effort to develop any estimate regardless of size, repetition and standardization benefits in larger projects. Indexed relative to Class 4 estimate for a $1 million project. $1 million, index equals 1.0, $10 million, index equals 0.28 to 0.74, $100 million, index equals 0.17 to 0.2. Larger projects also tend to utilize more advanced tools and better defined scopes, increasing estimating efficiency. 3. Variation with process or technological complexity. Projects with advanced high-risk or first-of-a-kind process technology demand greater estimation effort. Increased time is spent on custom scope quantification, specialized costing, additional review and validation loops. Complexity multipliers range from 2.0 times to 3.8 times relative to normal complexity baselines. High complexity is especially relevant for pilot plants, multi-stream chemical units, and aerospace nuclear installations. 4. Variation with estimating organization and team structure. The number of estimating subgroups, e.g. by discipline, scope area, or package, significantly affects effort. Larger or more distributed estimating teams increase coordination overhead, review cycles, integration and version control efforts. Relative effort indices normalize to 1 estimating subgroup, 3 subgroups, 1.9 to the 3.0 FEPS, 6 subgroups, 2.9 to 6.0 SEG. This variation often offsets economy of scale gains in large projects. Summary. The apparent inconsistencies in estimate preparation cost data are largely explainable through 4 dominant factors: project definition level, size, complexity, and team structure. Each variable introduces unique effort drivers, some reinforcing, others counteracting. The overall cost to prepare an estimate is the product of these influences, not a simple linear function of project scope or class. Estimators must account for these dynamic relationships when planning, budgeting, or benchmarking their estimating function, especially in capital-intensive process industries, where even small inaccuracies in estimation effort can cascade into significant downstream impacts.